I'm going to introduce our speaker. I'm going to give a much shorter introduction than Prof. Maru gave for me. She's to go on forever. But Chris is a UCT graduate as well. He did his BSc at UCT before shifting to do his honours in atmospheric sciences, but as a joint computing atmospheric science topic. And then he did his PhD also in the climate system analysis group at Environmental and Geographical Science, and that was on regional climate processes in Southern Africa. He's been working in a number of different roles at the climate system analysis group since 2000. He's the guy who makes all the computers work, but also does pretty amazing research all on his own. So he has this dual job, which everybody really appreciates. And I guess over the time that I've known quite well since I came back to UCT, his research interest has really been focused around the generation of climate change information that's actually relevant and usable and useful to climate change responders, if you want to call it that. So people who need to use it to respond to climate change, whether in the city of Cape Town, in agriculture, in whatever domain of response we're talking about. So a couple of things he's been involved with recently is a project called the South African Long-Term Adaptation Scenarios, which is really a national scale process of understanding what the climate risks are at a national scale, getting down to provincial scale. Chris was sort of the lead person on doing all of the analysis of what the future projections are in terms of climate for that. And then doing similar work with the city of Cape Town. So really helping the city of Cape Town understand what the future might hold. And that's really going to be the focus of some of his talk today. So it's going to be building on that work. So without much more to say, Chris, over to you.
Thanks, Mark. I think everyone should have an introduction like that every now and again, because it boosts your ego. This feels very loud. Is it very loud? Is it fine? Okay. It's ringing in my ears. So. It was very nice walking down from Upper Campus. There's a lot of steps on campus, in case you haven't realized that yet. So walking down all the steps from Upper Campus and looking across towards the mountains and not being able to see the mountains because of the rain falling. So it's very appropriate, I think, that we're talking about climate in Cape Town today. Okay, sorry, let's get this going. I'll put that other thing up as a pretty picture, do you? Okay, come on. Right, technology. I run all the big computers, but I'm often quite bad at PowerPoint, so excuse me if I'm wrong. Also, apologies, I'm recovering from a cold, so if I have a small coughing fit at some point, just talk amongst yourselves while I recover. So the title of the talk is Climate Change in the City. And the subtitle was A City Forecast, which is an interesting subtitle. And we'll come back to that a little bit, because it's not really a forecast. It's a projection, a set of projections. It's looking into the future, which is a little bit different. But I thought I'd start with an actual weather forecast. I always wanted to be a forecaster. Often when you tell people that you work in climate or weather, they think that you're the guy that stands in front of the TV. So this is my opportunity to stand in front of the TV and point at things moving. This is a satellite image from when I got to work this morning, after having cycled to work in the rain. And you can see, if those of you can see, I'm short, so I'm going to have to point like this. You can see Cape Town up there, up there. And the first of a double front, sometimes we get these double fronts coming over Cape Town. So the first part of the front hit us in the early morning and we got a bit of rain, including when I was cycling to work. And then you can see this thin second front arcing off to the left. And that's what caused the rain just now, just before I walked down to the lecture. So it's a very beautiful double front. You can look at it, that's what it really looks like. This is what it looks like through some different eyes. This is looking at water vapor in the atmosphere. And these are the kind of things we can look at to see what's coming towards Cape Town in the next few hours, sometimes even up to the next few days. So if I would issue a forecast, I'd say a small cold front is busy slipping past the south of the country. It's not hitting us like it does in winter, because in summer they're far south, it's slipping past the south of the country. It's bringing light showers to Cape Town and into the mountains, which is obviously where we need the water. And then conditions as the front passes, will continue to clear. And by Thursday, we'll be back up to nice hot temperatures, if you like hot temperatures. Right, so that's my small moment of fame as a weather forecaster. So we all live in the city. I wanted to start off by saying, who has been living in Cape Town for more than 10 years? If you can put your, wow, okay. A bunch of Cape Townians here. I'll put my hand up as well. Okay, who's been living here for more than 20 years? Okay. Who's been living here for more than 30 years? Wow. Okay. Okay, yeah, we're going to go big. Who's been living here for more than 60 years? Okay. Cool. Okay, so let's say in climate science, we typically say you need to look at least 30 years before you can start picking up a trend. So if those of you who haven't lived in Cape Town more than 30 years, you can't participate at this point. So if you've been living here for more than 30 years, who of you say that Cape Town is getting warmer? A few. Okay, that's interesting. Does anybody think Cape Town's getting cooler? Just out there? No. Okay. Now the interesting one. Who of you think that Cape Town is getting wetter? One. Okay. And who thinks Cape Town's getting drier? Okay. And who thinks it's exactly the same as it's always been? Okay. No, that's very interesting. Cool. We'll look at some numbers just now, which aren't necessarily a fact. They're alternative facts, for those of you who are familiar with alternative facts. Okay. So we live in Cape Town, which we all know is a very beautiful city, but it's also really complex and it's a diverse city. So when it comes to climate science and the impacts of climate and weather, it's also a really, really interesting city, and sometimes quite a devastating city as well. So we have scenes like this, the beautiful winelands, which are also key parts of our economy, producing high-value crops such as wine, table grapes, citrus fruit, not citrus fruit so much, but other types of fruit. These are high-value crops. That's an important part of Cape Town's economy. So that's part of Cape Town. We have beautiful areas like this. I think that's Groot Constantia. Yep. So it's a very beautiful part of Cape Town, but exposed to climate and weather changes. So already a lot of wine farmers are finding that temperatures are increasing, according to them, and getting too high for certain types of grapes. So they're looking at changing their types of vines, which is a very expensive thing to do because vines have a very long life and you have to plan a long time ahead to do that. Of course, we have the other side of Cape Town, which is a stark reality of flooding on the Cape Flats, informal settlements, people building houses out of desperation in areas that are not well suited to housing, lack of infrastructure. We know all of these challenges, and every year, time after time, these areas are flooded when it rains in winter. So it's very important that we understand what causes the flooding, how that might change into the future as we try and plan and implement infrastructure in those areas. Also in summer, the flip side of living in a shack in summer when it's 35 degrees outside and can be 10 degrees hotter than that, 15 degrees hotter than that inside the shack. So there's researchers at UCT looking at alternative ways of building shacks. We're also a port city. So we have a very successful and busy ocean port, which is also an important part of the local economy. But that port is vulnerable to weather. So the container depot cannot operate when the wind speeds are too high, and that really loses days of business through a year. There are other changes in the shipping industry as, for example, the Northern Passage opens up. These are long-term possible changes that might impact Cape Town's economy. And then, of course, we have the dams. This is a devastating image, but this is the kind of thing that we're seeing in our dams at the moment. And this would be the critical thing where Cape Town is vulnerable to a change in climate or weather patterns. We're experiencing that at the moment. This is such a topical topic as our dams run dry. And something that we're putting a lot of effort into, and the city of Cape Town is putting a lot of effort into thinking about how we deal with this in the future. So these are the contrasting and stark realities, and there's far more related to industry and economy that relate to the city of Cape Town. So what is Cape Town? When we were tasked by the City of Cape Town to look at climate change and the city and implications and impacts and projections, the first thing we had to do is sit down and say, well, what is Cape Town? Where does Cape Town start and stop? For some people, Cape Town is the city bowl. That's where they live and work. That's where everything happens. For other people, it's life out on the Cape Flats. For a water manager in the City of Cape Town, it extends right out into the mountains. So most of our dams are sitting out in the mountain areas, even going quite far north. For the local agricultural, it extends north into the Swartland. There's the Overberg region with the fruit markets. So the Cape Town is quite a dynamic thing, depending on who you're talking to. When it comes to making decisions, obviously we have the municipal area, which is in grey there. But again, that's dependent on the broader region. So we're very much in a lot of our work with the city, but also in other work that we're doing, we have to start thinking about cities in their context of a codependent region. A city doesn't operate in isolation. We have to ask a lot of questions. Where does our water come from? So in the City of Cape Town, the water largely comes from dams, largely in the mountainous areas. To some extent, we're drawing water already from groundwater. We'll talk about that option later. Water reuse, and then ocean desalination is an option that's on the horizon. For other cities, we're working a lot in Lusaka at the moment. 50% of their water comes from groundwater. The other 50 comes from the Kafue River. The problem with the groundwater in Lusaka is that you have to pump it out of the ground. And to pump it out of the ground, you need electricity to drive your pumps. So where does the electricity come from? It comes from hydropower, from the big hydropower dams, the Kariba Gorge. But if there's no water in the Kariba, there's no hydropower, you can't pump your water. So water becomes a really complex driver of risk in cities, a really complex factor. So it's a nice example of how when you start looking at climate and city, you need to be looking out into the region. Where do the resources come from? Where do things flow into the city? And how do they get there? Where does our food come from? There's a lot of discussion in Cape Town around food security. Those of you who are familiar with the Philippi agricultural area and the debate around developing that, so some of our food comes within the city. So we need to provide water to that agriculture. But a lot of our food actually comes from far outside the city. Some of it comes from the Swartland and the Overberg region, but some of it comes from Johannesburg, Gauteng, the Orange Free State. It's processed, it gets shipped around the world. Our chicken might come from India, it might come from Mozambique, maybe it comes from America if they sort out the trade deals. So the question of where our food comes from is often quite complex. So if there's a drought in China or India, that can impact us as rice prices go up. It's a complex picture. Where does our power come from? So for the large part, City of Cape Town power comes from obviously outside of the city now. We used to have power from within the city in Athlone, but now it comes from outside. Some of it's from nuclear, some of it's from upcountry, the big coal power fire stations. Those power stations are also vulnerable to climate change because a lot of them are either air-cooled or water-cooled. If they're air-cooled and the temperature's going up, you have impacts. If they're water-cooled and there's drought, you also have impacts. Another interesting one that people talk about often is climate migration. I wouldn't say that Cape Town's yet a recipient of climate migration. It's often very difficult to unpack climate migration from other types of migration. But people do begin to move areas. If there's extensive drought in one area, after time, people will start to move out of that area. There's already a natural urbanization as people move from rural areas into cities. Sometimes that can be driven more rapidly if there are climate changes. And then a very complex one is the economics. I'm not an economist, and there's good reason for that. I'm probably not clever enough. It's a very complex system, but in the City of Cape Town, tourism is a big part of the local economy. And how does weather and climate impact tourism? There's already some discussions about how high temperatures get before tourists stop visiting a city. It's particularly coming into play in the Middle East. High value agriculture I've already mentioned, and then the trade port. So the picture I'm trying to paint here is that climate and weather in a city is a very complex picture, and it can extend from the local scale, living in a shack really, really hot, or water coming through your door, through to a global scale where you're dependent on international food markets and trade dynamics. So it's a very complex picture. For this particular study, we didn't go to the global context because it's just too complicated. We extended it to the regional context, particularly the water catchment regions in the mountains. But we always have to keep in mind the bigger picture. So I have no idea what Mark lectured on yesterday, but I'm sure that he covered everything that you needed to know about the global climate system and how it might be changing. But I thought I'd just quickly flash this image up, which is a schematic, if you like, of the global circulation patterns. And the particular one of importance is what we call the Hadley Cell and the mid-latitude cell. And the city of Cape Town sits obviously southern tip of Africa, and it's in a really interesting position because it's between two large circulation systems. You have rising air from the equator. It rises because it's getting warmed, and it descends into this high pressure zone here. Combined with that, you have the westerly wind patterns going round and round the world from the westerly to the east, and Cape Town sitting in the middle there. So most of the time we're dominated by these high pressure cell caused by the descending limb, as we call it, of the Hadley cell. Yeah? So there's high pressure, and high pressure means the air is subsiding, which means you get clear skies, you get nice warm temperatures, really good weather. But sometimes, like today, a westerly wave moves north and hits Cape Town. And I think I've got that slide there. Yep. This is what it looks like. So if you can't see, these projectors don't work, but Cape Town's up there somewhere. Hope you can see the map. And you can see the westerly wave. It's a wave in those westerly wind belts. And that westerly wave is hitting Cape Town, and associated with each of those waves, you get a band of rain. So that animation I had up at the beginning, you could see those bands of rain. And that brings rain to Cape Town, into the Cape Town mountains. And that dynamic of largely dominated by that high pressure system, and then the westerly wind belts and these westerly waves periodically hitting Cape Town and bringing rain to Cape Town and into the mountains. That's essentially summarizes largely Cape Town's weather. It's probably as much as you need to know at this point.
Why do we get rain in winter? Is it more wet?
So I'm glad you asked that question. So this pattern is the kind of default pattern, but as we go from summer to winter, the whole system moves north and south because of the Earth's tilt. So in summer, the Earth tilts such that the southern hemisphere is more exposed or more directly impacted by the sun. So all these patterns move south, and the high pressure systems move south and dominate Cape Town more. And the westerly winds move further south as well. So those waves in the westerly winds can't hit Cape Town as much. In winter, the reverse pattern happens. So that all these patterns shift north, and the westerly waves begin to hit Cape Town, and we get the rain in Cape Town in winter. Does that explain it? So everything just moves north and south as we go from summer to winter. Okay. Obviously, we do get cold fronts in summer. We're getting touched by one now. We've had major cold front events happen. I remember one Christmas Day we had a big cold front hit Cape Town. So it can happen, but the frequency and the intensity is much more regular or much stronger in winter. But we'll talk about these shifts later because these are the primary processes that we want to look at when we look at climate change in Cape Town. Are there any other questions on that? Everyone happy? Cool. Okay, so we can start looking at what's actually been happening in the past. But straight away, we hit an interesting problem of how do we observe the weather? How do we observe climate? And the traditional way of observing climate is we have weather stations installed. So we have weather stations sitting somewhere, and every moment in the modern weather stations, they're sampling every few seconds. But in the past, someone would go out every day and take the readings. People are still doing that. Some of our best records come from farmers who every day go out and take the measurements from their weather station. So we can take those weather station measurements, and over many, many years, we do like to look over a long period of time, and I'll explain that just now. We can begin to paint a picture of what the average climate is, but also how it might be changing. The problem is, and the devastating challenge that we're struggling with at the moment, is that the number of weather stations available is declining very rapidly. So there's lots of ways of looking at this. This is one way that we produce for the city of Cape Town. This is a number of weather stations on the y-axis that contribute to a mean rainfall record for around the city of Cape Town. There's lots of ways of looking at it, but So back in the 1900s, we had maybe 30-odd stations that increased all the way through to the 60s, 70s, 80s, where we had 40-odd stations in the region. And then rapidly it's declined, where we've now got 3 or 4 stations in the immediate region of Cape Town that are regularly reporting. And the picture is the same across the world, actually, but it is particularly acute in Africa. South Africa definitely has the most dense station network in Africa. We've managed to maintain things better than a lot of countries, but it looks like this across most of South Africa as well. So it makes a real challenge for analyzing long-term changes in climate. And as that goes into the future, it's going to become even more challenging. Yep.
Why the decline?
Largely it's financial. So there's been a lot of budget cuts to try and limit that. There's also been a shift. So a lot of time farmers would keep their own records from their own weather stations. There seems to be a decline in that, or else there's a decline in that data making it into the official records. So actually we're often approached by farmers and say, I've got 50 years of records from my farm, but I don't know what to do with it. And it is challenging because it often is handwritten on pages of a notebook. So, we then might have to pay a grad student to sit and type it all in. So there are challenges like that. There are a lot of big efforts at the moment to try and recapture archive data like that, but it is challenging.
Is it not because satellites are doing a lot of the work?
So that's, yeah, I'll come back to that. But satellite observations have tried to replace that, and to some extent they can. But even satellites, you still need to calibrate them against actual observations, and there's also strong limitations. I'll give you an example just now what satellite data does. So we have this problem, which is, it is significant, and we need to deal with it. We've, as a university in our particular group, we've installed a series of weather stations. It was actually installed in order to monitor fire in the Fynbos regions. So this is our current map of stations. You can see where the little markers are. This was this morning. There are some problems with this data. It's not really minus 39 up on that mountain there. But we just before the lecture, I was having a discussion about we install all these stations, but there's no funding to maintain them into the future. So at the moment, it looks like the network will die unless there's funding. Okay. But we do have some observations, and those tell us, okay, everything's got shifted here. All right. Those tell us some really interesting things. For example, this one was meant to point to the airport. All the arrows are shifted down slightly. But the airport gets, on average, 520 millimeters a year through the winter rainfall season. Sitting in Kirstenbosch, we get 1,285 millimeters. Going over to near Jonkers, just north of Theewaterskloof Dam, 998 millimeters, and up near Malmesbury, 363 millimeters. So it's a very diverse climate. There's a huge range in the amount of rain that falls. So when we were looking at this, we had some problems with data. Lack of station data. The one that I'm going to whisper is that we also don't have permission to use the official South African Weather Service data. This is off the record. There's some interesting challenges with actually getting permission to use that data. So we ended up using a proxy data product that uses some station data, but it also uses some other methods, including satellite data, to try and merge messages together. We've selected this one. It's called WFDEI. It doesn't matter why, but it is. And what we did is we broke up that area around Cape Town into different climate zones. So you'll see the different colors on the map on the left. And this plot in the middle is the monthly, going from January to December, the monthly rainfall in each of those zones. So you'll see that northern zone, which is the west coast, is the driest. The Cape, particularly around Cape Mountains, is the wettest. The Swartberg is in between that, and then the Overberg. So those are the different regions we identified. And the very far right there is the time series of annual rainfall from 1981 through to 2009 in each of those. So you can see there's quite different rainfall in each of those places, but through time it kind of agrees with each other. So wet years are wet years in most places, except for the West Coast region, which is doing a little bit of its own thing. And now we can take each of those regions and we can look. This is a very long record from another data set. It actually goes from 1900 through to the present. So this is 100 years estimated rainfall for Cape Town for those 4 zones that we're looking at. Give you a moment just to take it in. Can you see? Is it difficult to see? Can we turn lights off, do you think? Is it? Does that help? Okay. Okay, it's very difficult to see, so I'll tell you. I'm also colorblind, so if I name a color wrong, it's not my fault. So what you can see is that the Swartland, which is it yellow at the top? Yeah. Okay, excellent. I'm getting better. My kids are slowly teaching me my colors. So yellow is showing a very slight drying, a very slight decrease through that 100 years. Cape Town is also showing a very slight decrease. So is the Overberg. But the West Coast is actually showing a slight increase. But these are really, really small changes. So you could argue that those of you who answered my question in the beginning, is the rainfall staying the same, were probably correct. But as you can see, the wavy line, that's the long-term variability. So that's where we take 10 years at a time, we take the average for those 10 years, and then we shift along by 1 year, calculate the average for those 10 years. We call it a 10-year running mean. So it's the very long-term variability, and it varies a lot. So you definitely get dry decades and you get wet decades. And this is why it's often very difficult to say that we're experiencing climate change or we're not, because we have this long-term. Sorry? Yeah, sure. Do you want to see me? Okay, cool. So there was a question earlier about satellite data and other data sets. When we first started working with this, the data set of the moment was called CHIRPS, which is actually quite a good data set in many areas. So we automatically thought we'd use it for Cape Town, and we calculated the trends for the last 30 years or so. And this is the trends that came out of CHIRPS. And that immediately raised red flags, and we decided, and after another analysis, we decided this data set is no good. So it's just a red flag to say when you're looking at past observations of anything, you have to be really careful about what you're looking at and that the data is actually representing reality. Cool. Right, sorry the numbers the fonts are so small here, but we can also break it up into some different statistics. So the top one is total annual rainfall for the last, from 81 through to 2015 or so. So not much happening there, but there are subtle differences. The one in the middle there is the mean daily rainfall. So that's on average when it rains, how much does it rain? So it's kind of an intensity measure. And there are some negative trends there. The bottom one here is the number of rain days. So I know anecdotally a lot of people have said to me that there's more wet days in Cape Town. It's not necessarily raining more, but there are more days when it's actually a little bit wet. And there's some indication in certainly in the last few years, that some areas have shown that kind of change.
Which one is Cape Town?
The blue one is Cape Town. Yeah.
Blue, which is blue?
I believe this one's blue. But is it purple? Okay. We all have our version of reality. Okay. We can also break it up by season. So the top plot here is for summer, December, January, February. The next one down is March, April, May, which is autumn, beginning of the rainy season. The next one down is June, July, August, and the bottom one is September, October, November. So one of the shifts that we are starting to see is a drying of autumn and possibly an increase of rainfall in the middle of the winter season. So particularly if you look in the last few years, there's been an increase in the middle of the winter rainfall, but a drying in the early winter rainfall. But these are all very tenuous trends. I wasn't going to go through all the statistics, but the maps on the left there, if there's a little cross, it's what we call statistically significant. And that basically means that we can say with some level of confidence that the trend we're seeing is not just natural variability. There's actually an underlying process driving that trend. We're not necessarily saying it's climate change, but climate change would be the obvious culprit at this point. Okay, So there's a lot of graphs there. Apologies, they're difficult to see. We can make these available. But yeah, some quite interesting stuff. Temperature is much easier. This is the last 35 years of temperature in Cape Town, across Cape Town, the same regions. And you can see the top is minimum temperature, so those would be nighttime or very early morning minimums. And the bottom is maximum temperatures, so midday or early afternoon temperatures. So across all those regions, there's positive trends. The strongest trends tend to be in the minimum. That's something that we do see globally, and there's a physical understanding or process behind that. But it is pretty clear that Cape Town has got warmer. So those of you who answered that in the beginning, I would agree with you. Okay, so now, what about the future? So that's what's happened in the past, or what we think might have happened in the past. Now we want to look at the future. So how do we do that? And again, it comes down to this schematic, these large-scale global processes. Now, the process sort of story behind climate change is that there is increased heating, and a lot of that heating is increasing or focused on the tropics, around the equator. And what that does is it increases the intensity of this Hadley cell circulation. Okay, so that circulation is stronger and more intense and shifting further south. So whereas this would be 30 degrees in this picture, it starts shifting further south. The consequence of that is that South Africa and Cape Town becomes more and more dominated by that high pressure system, which suppresses rainfall, which pushes those westerly waves further south. And we should, in theory, according to the sort of process understanding, we should be getting drier in Cape Town, or we should get drier in Cape Town in the future. So that's one way we could do it. We could say it's a thought experiment. We don't even need a model. We know how the large-scale global circulation patterns work. We know how they respond. So as a thought experiment, we can say it should be getting drier in Cape Town. But no one believes the thought experiment, so we can start looking at other observations. These are, for example, observations of different indices. The top one is called the Antarctic Oscillation, and the bottom one is the Southern Annular Mode. These are essentially ways of trying to measure that shift in the Hadley cell, the shift in where those mid-latitude waves are centered. There are two ways of doing it, and they both are showing positive trends. They're both pointing towards those westerly shifting south, the dominance of the high-pressure system. So again, there's a little bit more evidence to say we should be getting drier in Cape Town, and it's likely that this would continue into the future. But of course, what we must do, if we're true scientists, is build a model. So I'm sure Mark spoke yesterday about building models and what models are in climate modeling, and this was the coolest schematic I could come up with of a model. So a climate model basically chops up the Earth's atmosphere into these lots of little blocks. In each of those blocks, it solves all the fundamental physical equations that we understand about how the atmosphere moves around and changes. And yeah, and we do that, and we can then simulate the Earth's atmosphere for hundreds of years or even thousands of years. We can then change things. We can add CO2. We can add aerosols. We can make volcanoes explode. We can change solar cycles. We can do all sorts of things with those models and see how the modeled atmosphere responds. Of course, it's just a model. The very early models, again, Mark might have shown this figure. He didn't, okay. The very early models were very, very simple. We didn't have the big computers we have now. So in the first assessment report, for those familiar with the IPCC, doesn't matter, this was quite a while back in the 90s, that top figure there is how the models saw Europe. So, and over to Greenland on the top left there. So you would hardly recognize Europe. That's how the model saw it. Each of those grid boxes was about 500 kilometers across. So it's pretty coarse stuff. Then the next sort of evolution of models, they halved the resolution, so down to 250 kilometers. And you can start seeing the Mediterranean, the Black Sea, Scandinavia, and this is actually England and Ireland, but it's still very, very coarse. And then as it developed, the next series, top there, and then this one, this was actually AR4, which is previous generation, but actually things haven't changed much since then. So you can see now Ireland and England are pretty separate. You can see Europe. You can see the Himalayas, gosh, the Alps. and across to Greenland there. So you can see the current generation of models are actually capturing a lot of the features fairly well. But each one of these represents a different model that we work with. So there are a lot of models. We're working most of the time with these 16 different models. There's actually more like 50 different models to work from. Different research groups, different institutions around the world build their own models. They make their own assumptions. They make their own solutions to the equations, different ways of doing it. They capture things in different ways, and they produce different models. And each of them run simulations of the future. So we end up with a whole spectrum of simulations. This is the projected change in winter rainfall for South Africa that we did for that national project. And you can see that it varies. I'm not going to go into the detail there, but the point is that there are a lot of models to look at. It's also important to note that it's very difficult to pick out what's happening in Cape Town from these kind of plots. Okay. We're often asked if some models are better than others. Why don't we just pick the best model? And this is a huge area of research within climate science, climate modeling, is can we say one model is better than another? The politics, if you like, science politics of that are actually changing. I've seen it change over the last 10, 15 years. 15 years ago, people were using single models. Then it became very common to try and use all the models, the full ensemble. Now there's more and more discussion about saying we need to be able to say that some models are better than others. So for the city of Cape Town, we developed this very convoluted method that every time I look at it, I have to rethink it to try and evaluate how well models are representing Cape Town or the Cape Town region climate system. So we had this complicated way of doing it. If anyone's interested in it, we can try and do it. And what we came out was on the right, where we evaluated the performance of those different models. And actually, they didn't vary very much. So we ended up using all of them. But it is a really interesting question. And it's one that we often get asked, is why can't you just pick the best model, or which is the best model? In fact, the city has asked us that. Which is the best model for Cape Town? And why don't we just use that? Because it would simplify things a lot. But we don't. At this point, it's very difficult to do that. I'm happy to take questions on that because I think it probably is quite interesting. So what we do is we take the whole ensemble of models, 16 different models, and now we've analyzed all those model projections for each of those 4 regions again, or sub-regions around the city of Cape Town. So these are what we call plume plots, and they're the projected change in total annual rainfall for those regions around Cape Town. And it's not a very good-looking picture. Basically, the color change is quite important. So I'm going to ask you, what is this color? Bluey purple. Okay. And this color? Greenish orange. Okay. So the bluey purple bits, wherever it's bluey purple, basically means that what the models are saying is not really different from natural variability. So nothing's really changing significantly over here. As soon as it changes to greeny, orange, whatever, that's when that model is starting to say that the climate is shifting significantly from what we've observed naturally. For those of you who can't see, this is 2011, this is 2031. So for most of the models, for a lot of the models, by 2031, they're saying climate is significantly drier than what we've observed in the past, which is quite a scary picture. So this is the scale as well. Cape Town, 350 odd millimeters a year. You know, if this model is right, by 2080 or so, we'd be down to 200 millimeters a year. That's quite a depressing picture. Yep.
Doesn't matter what we do.
This is using, okay, that's another whole kettle of fish. What? Can of worms? No, okay. So the reason this is a statistical thing. So the reason it pinches to a point there, I'm glad someone spotted that actually, is because that's our reference period is around there. So in the middle of that reference period, the models, there's no difference in the climate. That's our reference point, if you like. Well, we can look further at that, but it's these are quite sort of different ways of visualizing things, and that pinch point is bugging a lot of people. But it is just a consequence of the statistics. Yes, this is no matter what we do. So you'll see at the top there, RCP 8.5, that's a shortening of the representative concentration pathways. Did you talk about that, Mark? Okay. So you know about representative concentration pathways, so what the future emissions might look like. 8.5 is a very pessimistic, can I say it's a Trump world? It's a business as usual kind of world of industrialization. So quite large emissions going into the future. We used it here because it pulls out the signal quite strongly. We also do the same for 4.5, which is a much more conservative projection of emissions. So this is a very negative view. This is probably the kind of worst case scenario, depending on your view on humanity. Yeah. Okay. So that's quite a negative view. This is looking at the amount of rain that falls in extreme events. It's slightly subtle statistic, but it's basically looking at heavy rainfall and how that might change. And in a way, this might be a good picture for flooding in Cape Town, because it's really saying that the intense events will become less common, or less rain will fall in the intense events. Temperature is equally concerning. So like most projections in the world, temperatures are projected to increase quite significantly. So Cape Town at the moment, the mean temperature through the year might be, I guess that's around 19.5. By 2031, we could be anywhere between 20 and 21 degrees. And I know 1 or 2 degrees doesn't seem like a significant change, but a hot season versus a hot summer versus a cold summer is often only a difference of 0.2, 0.3 degrees difference. So you would experience that as a really significant change. And then this is the number of days that exceed 35 degrees centigrade, which is quite a common sort of discomfort measure. 35 is quite an uncomfortable day. I'm sure many of you will agree. On the West Coast, they currently get about 10 days a year that exceed 35 degrees. By 2050, some models are saying 30 days a year would be exceeding 35 degrees. Now, downscaling is the next thing that everyone wants to talk about when you talk about urban climate change. This is really responding to the fact that those global climate models that produced those graphs before are still very coarse. So they might, again, have box sizes of 150 kilometers, which is the distance between here and Hermanus. It's quite a coarse scale. So are they really capturing the local climate system very well? Are they capturing the mountain topography and how that affects the climate? Probably not. So what we do is downscaling. Now, those are cirrus clouds. And for those of you who lived in Cape Town a while, you may recognize cirrus clouds are often precursors to rain. And that's because cirrus clouds are formed in the high jet stream. As that jet stream wave moves north across Cape Town, you get these cirrus clouds, and following that high jet stream wave, you often get the cold front that produces rainfall. And in a way, if you make that association, has anyone made that association? Mare's tails and there's rain coming. Okay. I was explaining it to my kids the other day. That's why it was topical. When you make that association, essentially you're downscaling. You're looking at the large scale picture and you're saying, I know what happens at the local scale. And there's two ways of doing it. There's statistical, which is what I've just spoken about, where you can look at past observations. You can say every time this happens, every time the wind shifts to the north, which is another precursor of cold fronts, we know that it's probably going to rain in Cape Town. We do it in a more statistically objective way, but it's basically the same idea. We can say every time this large-scale pattern shifts, we know what happens in Cape Town. And we can do it down to the point scale. So we can say we know what happens in Newlands versus what happens at the airport, and they are different. So that's the power of downscaling. But we can also do it dynamically, which is essentially the same as those big global climate models, but you can run a regional climate model where you don't try and simulate the whole Earth, you just simulate a really small part of the Earth. So you could take the Western Cape, and you could just dynamically simulate, just like that GCM does, but you just do a small region. And because of that, because it's a small region, you can do it at a much finer scale. So we routinely do downscaling, dynamical downscaling, down to kilometer scale. And you can start capturing some of the dynamics. But it is really expensive. You need really big computers for a long time, which is my job. So we do try and do it, but it's hard. So a different picture. Now we're going to throw the cat among the pigeons. No, I'm not good with my metaphors today. Whatever. This is what happens when you statistically downscale those global climate model projections for Cape Town for total annual rainfall again. So it's quite a different picture. The statistical downscaling for these 4 regions shows anything from some marginal drying through to some marginal increase in rainfall, and a lot of the time it's still bluey purple, which is saying it not significantly changing into the future. And this really threw us when we started unpacking these results. Yep.
Haven't you reversed SWOT clouds and overbird?
Might well have. Is it important? Swartland. Oh, then you mean the magnitudes? Oopsie. Whoa. I've just lost everything. Sorry. Sorry about that. Yeah. Yeah, we got there. We're getting there. Okay. Okay, let's pretend that didn't happen. Okay. If the labels are wrong, we can deal with it some of the time. But the point is, it painted a very different picture. And this raises the last thing I want to, or second last thing I want to talk about, is the mountains around Cape Town are really complex. How many of you regularly hike in the mountains? I thought so. Okay. So those of you who hike in the mountains will know that even if it's not raining, if there's cloud on the mountains, the vegetation can get really wet. You also know that it can be a beautiful sunny day in Newlands, you go up the mountain and you get wet in rain. And these mountain climate dynamics are really significant and they're really important, but they're not well observed because we don't have weather stations in the mountain, and they're not really well understood. So one possibility is that the global climate models, they're not able to represent those mountains very well because they're so coarse, but the downscaling can capture some of those local scale dynamics. There's some physical basis for saying that rainfall in the mountains might increase in the future as the atmosphere gets more moist. Moist air flowing over the mountains can produce more cloud and rain in the mountains. Even just cloud droplet capture. There's some estimates that on some of the mountains, like Silvermine, they did some tests where up to 50% of the precipitation, so water getting into the soil, actually doesn't come from rainfall. It comes from cloud droplets impinging onto the vegetation and dropping down. So it's a really interesting dynamic that we don't fully understand. Okay, so lastly, we had all these results and we had to communicate them to the city. And this is probably the hardest part, and for me, a lot of my research is now in this area of how do we actually communicate this kind of science, these kind of results to decision makers. And it's really hard. And one of the biggest challenges is that uncertainty is hard for decision making. If you presented with those previous plots saying rainfall could go either way, what do you as a city water manager do about that? How do you deal with that? I've shown you lots of graphs and maps today, and they're easy to misinterpret. They're hard to understand. If you're reading it in a report and you don't have someone to explain the details and the nuances, they're very easily misinterpreted. So one approach we're trying is telling stories. Everybody likes a story. It's a natural human way of communicating complex things, is to tell stories. So we're exploring a storytelling approach to telling climate change information. Are they true? The best stories are never true. So or there's truth in every story is another way. So I'm not going to read through these, but for the city, we developed these 3 different alternative truths. We developed 3 different stories because we don't know which one is true. But it's interesting, the process of developing a story, the process of telling the story, the process of getting feedback from people hearing the story. It becomes a discussion, it becomes a conversation starter. And that in itself has become a really interesting process of communicating with decision makers. That's just the end of the third story. I just pulled this out as an example, but we're running short of time. So the idea is to tell stories that weave in climate, that weave in other things, that weave in farming, that weave in poverty, that weave in economics. And as we slowly develop these stories with the city, they begin to tell a rich story of what the future of Cape Town might look like. And we have, at this point, 3 different stories of what the future might look like. Maybe some of them are more likely than others. We've yet to determine that. But it's an interesting process, and anyone interested in that can chat further. I wanted to pretty much end with this slide, which is the last paragraph that I wrote for that City of Cape Town report. And it's probably been the most quoted and maybe contentious. But I'll just read it out to you for those of you tired of reading. What the reports and the narratives, and we did a workshop, have all shown is the City of Cape Town needs to prepare in earnest for a drier and a warmer future over the next decades. There remains uncertainty. There will remain uncertainty. But the evidence for drying and warming is strong. And planning that ignores this evidence is a significant risk of vulnerability to a changing climate. There is now sufficient scientific evidence to motivate for serious consideration of climate adaptation planning and implementation in the city. What is the city doing? I'm not going to go into that now because it touches on... Do you want to? Okay. Helen's going to talk to you tomorrow about what the city is doing, but just very, very briefly, there are plans. It's a case of when, not if, what those plans will be. Did you know that we're actually using the same amount of water as we were 15 years ago in Cape Town? And most of that is because of demand management and fixing of leaking pipes. We're actually world leaders in our leak rate at the moment. We're about as leaky as London, and they've been doing a lot as well. But those interventions, if you like, have kind of reached their maximum.
Is that just in the plus? In other words, are we getting more leaks? Is London and us both adding leaks?
London was pretty leaky, but they've done a lot. Yeah, leaking is bad. That's a loss of water. So we've done a lot of work to reduce leaks. Yes, population and demand will grow. And I suppose the key message out of that is that even without any climate change, we're going to need alternative water sources. So there's a lot of work looking at the projected demand. So we're currently sitting here. That's the demand going through to 2030. So from 600 million cubic meters per annum up to 900 million cubic meters per annum in 2030, which isn't too far away. Those are the kind of projections. The other lines are the different sources that we can implement. And this projection is if there is a reduction in rainfall in the future, which is why the dam yields reduce into the future, the Berger River reduces into the future. And these are things like groundwater extraction, water reuse, and right up at the top in the red is desalination. But Helen will cover this tomorrow, I'm sure. I'm also happy to take questions. Okay. And I'm going to end with this graph, which is the last 3 years of rainfall. There's been a little anecdote going around that the last 2 winter seasons actually haven't been dry and that the dams are empty because of mismanagement. I just wanted to say the last 2 winters have been dry. I pulled this data out yesterday. It's the most recent up-to-date data. 2014, we got 506 millimeters, which is 97% of average. 2015 was 63% of average, and 2016 was 68% of the average. So it has been dry, and that's pretty much why the dams are empty. Okay.
Your models forecast for 2017.
I knew that was coming. I don't do forecasts. We do seasonal forecasts for the winter season, but there's very, very low skill in those forecasts. We have regular debates in our group, and it's very difficult to predict winter rainfall season. Summer rainfall, there's some ability, but winter is very hard. Sorry. Okay, lots of questions. Yep.
Can you paint a word picture of what it's going to be like to live through that scenario you showed us? I mean, with all the increasing heat, how's it going to affect anything from our daily lives?
Yeah, I mean, that's sure. There's a whole lecture in that. Everything from personal life, depending on your circumstances. So as usual with climate change, the wealthy can probably adapt. You can install air conditioners, you can do things to adapt. The people that get hit are those that are living in poverty who don't have the options. But there are lots of implications on local agriculture, even on water. So one of the big things with water is that higher temperatures increases evaporation from dams. So you don't necessarily need a reduction in rainfall to reduce water resources. I think Mark will talk more on Friday about water in Cape Town. Health implications, there's whole avenues of research looking at the impacts of what that would look like. Yeah.
They're just thinking it's just going to happen, or they're doing something?
There's plans in different sectors. We're working currently on 3 different projects funded either by national government or local government that are looking at plans and things to implement. So again, Helen will talk about the city tomorrow. There's definitely plans in action. It's often it's a case of allocating resources. You know, a game we often play is getting people to decide, do you build more houses or do you build a new dam? You know, how do you balance those resources? So, but it's being discussed extensively now. Yeah, at the back.
I presume when you were talking about the high pressure moving further north and further south, beginning of winter and summer,
Yeah.
you have exactly the same phenomenon in the northern hemisphere, just the other way around.
That's right, exactly. Yeah. Yeah.
In that first real-time thing you had of the wind,
Yeah.
there seems to be a very stable ridge just south of us.
It's a.
Is that a permanent phenomenon?
No, it's a deceptive image. So it's actually one snapshot in time, but they do the movement to highlight where the features are. So it's moving through time. Yeah, it's not stable. Yep.
I was just about the boreholes.
Yeah.
Because like my state has it, and some people are saying that it's water that's just flowing out into the ocean, so it's fine to take it out.
Yeah.
Some people are saying it's horrible for destruction.
Yeah, I mean it's complicated. I'm not an expert. Mark's probably more an expert, but the question about boreholes: are they okay to extract water from boreholes? Does it have consequences? So what I can say is, in other cities, for example, in Maputo, we're working in the moment. They're doing a lot of borehole water, and because it's a coastal city, they're getting salination or salt water intrusion into the groundwater. So they're starting to pump salt water out. Those kind of things happen. You can get land subsidence in some circumstances. If you're tapping into deep water aquifers, then it can be fairly sustainable, but it needs to be well understood before it's implemented. Yeah.
There's a report came out just before Christmas which said that by 2050 all the world aquifers will be empty.
Yeah, there are lots of studies. I think it's a useful source. And there have been studies around the Western Cape aquifers, so we're going to have to resort to groundwater at some point. Yeah.
How does the El Nino affect those westerlies?
Yeah. That's a good question. We don't have a good understanding of that yet. At the moment, there doesn't seem to be a very good link, which is one of the reasons why forecasting the next winter season is difficult, because most seasonal forecasting depends on a link to El Nino. So there are possible links through the mid-latitudes, but they're not well understood. So at the moment, we generally say the Western Cape rainfall is not influenced by El Nino, though there may be some subtle linkages. Yeah. Right at the back. Oh. Records of?
What the lowest rainfalls have been and for over what period? Like we've had 2 years in a row now.
Yeah, I could bring them up just now. I'd have to get online, which I'm not sure I am at this point. So we have a web platform that lets you go and look at all that data. One thing I've been wanting to do is compare this with the 2001 droughts. Those of you remember those. I'm not sure how they compare at the moment. Sorry? Oh, okay, you'll see it on Thursday. But sure, come down and we can look at some numbers, yeah. Yeah.
The picture you had at the beginning from the Null School
yeah.
website, at what altitude was that?
That was 700 hectopascals, which is about 3,000 meters, okay. So wind, yeah. But it's a similar pattern at 5,000 meters. So those of you flying to Joburg tomorrow will probably get there quicker than normal. Okay, yeah. I don't know how long we keep taking questions, but.
The gardeners are all hoping for El Nino.
Sorry?
The gardeners are all hoping for El Nino to follow El Nino.
El Nino probably will follow El Nino, but whether that impacts the rain in Cape Town is very unlikely. So I'm not going to make a forecast about the next winter rains. One assumes that they will return to normal or be good at some point, but the possibility of 3 dry years in a row shouldn't be disregarded. Yeah.